Hi there, Miss Barber here. Find the relationship between the triangular numbers, that is, the sequence that consists of 0, 1, 3, 6, 10, 15, ... and an unknown sequence whose terms are 4, 9, 19, 34, 54, 79, ... When looking for a relationship between two sequence of numbers, I'm looking for a pattern, and I usually do that by looking at gaps. So let's begin by looking at the gaps for our unknown. By that I mean from 4 to 9 is 5, 9 to 19 is 10, 19 to 34 is 15, 34 to 54 is 20, and if the next one is 25. When we see that each term is increasing by 5 more than before. That doesn't seem real helpful, but let's just continue to see if we can find another set of gaps that might be useful. So now let's look at the gaps for our known. Okay? We know what they are, but let's just write them anyway. We go from 1 to 2 to 3, 4, 5. That ought to make sense if you're looking at the triangular numbers, right? Just on the top, triangular numbers. There's 1, 2, 3, and then we increase by 1 as we go down the triangle. Now, 1, 2, 3, 4, 5 does not look a whole lot like 5, 10, 15, 20, 25. So let's look at secondary gaps. Okay, that is, we want to look at gaps between the gaps of the first line of numbers. Let's see if we can find anything interesting there. So I'll go back to our unknown, and the gap between 5 and 10 is 5. The gap between 10 and 15 is 5. The gap between the next two is 5, and the next two is 5. What that tells you is that there is a constant gap on the secondary gap line. Let's see if that's of any value when we look at the triangular numbers. Well, the gap between 1 and 2 is 1. 2 and 3 is 1. 3 and 4 is 1. The next two is 1. Now, 1 and 5 are different numbers, but this is very encouraging because they are constants, right? And so we can make the 5 a 1 just by dividing by 5, but then that messes with all kinds of messy fractions. And I want the terms of a sub n to be multiples of 5. So now let's do some neat little algebra tricks. What I'm inclined to do here is add 1 to each term of the a sub n sequence. So what would that look like? Well, we'll have a sub n plus 1. Note, I'm adding 1 to the term, not doing n subscript plus 1. So if I do that, 4 plus 1 is 5. 9 plus 1 is 10. Then we get 20, 35, 55, 80. Now, why is that important? Because now we can divide by 5, and then we get that secondary gap to be 1. Let me show you what I mean. Let's take this, a sub n plus 1, divide it by 5. Then 5 divided by 5 is 1. 10 by 5 is 2. 20 by 5 is 4. 7, 11, 16. Now, before we get too excited, we're still off a little bit, right? Because the triangular numbers start at 0, but the gaps are now the same. So if we look at the gaps of this adjusted a sub n, then we have 1, 2, 3, 4, 5. This is exciting. It matches what we had for t sub n, except that the numbers are not the same. Yet, if we observe, we'll notice that it's just off by 1. Let me tell you what I mean. So let's suppose we look at a sub n plus 1 divided by 5, okay? Then I subtract 1. If I do that, 1 minus 1 is 0. 2 minus 1 is 1. 4 minus 1 is 3, 7 minus 1 is 6, 11 minus 1 is 10. You get the idea. 16 minus 1 is 15. We got it to match. So we have a sub n plus 1 divided by 5 minus 1 equals t sub n. Let's clean this up a little bit. I would write this as a sub n minus 4 divided by 5 equals t sub n. I got a common denominator in subtracting the 1. Then, hey, let's just go ahead and solve for a sub n. A sub n is equal to, multiply the 5 through, so 5, t sub n minus 4, so plus 4. Here we go. We found the relationship between the triangular numbers and the unknown sequence. Find the relationship between the sequence, t sub n, the triangular numbers, and an unknown sequence, b sub n. I always begin by looking for patterns, and that's usually done by looking at the gaps between the terms. I know that gaps between my triangular numbers, they increase by 1. So we go from 1, 2, 3, 6 to 10 is 4, 10 to 15 is 5. Now let's look at the gaps for the b sub n. 6 to 9 is 3, 9 to 13 is 4, 13 to 18 is 5. The next two terms is 6, so it's increasing by 1, sort of like a triangular number. The problem is it's still offset. So we need to figure out, how do we address the offset? Let's begin by adjusting it back 3. That is, let's look at the sequence b sub n and subtract 3. So we get a whole new sequence, and subtracting 3 from each of the terms. 6 minus 3 is 3, 9 minus 3 is 6, 13 minus 3 is 10, 18 minus 3 is 15, then 21. And so now we have numbers that match the triangular numbers, but we are still offset. So let's just pick a number and figure out how to make it work. I like to look at this sequence, okay? The first term, which would be b sub naught minus 3, and that is actually the number 3. Now, if we look at the 3 and try to match it up with a triangular number, that would be, let's see, t sub naught, t sub 1, t sub 2. That's equal to t sub 2. Now we are able to make a match. Let's generalize it from the first term to the second to any nth. So this will be b sub n minus 3 equals t sub n plus 2. And we can now solve for the unknown b sub n, and that'll be t subscript n plus 2 plus 3, and that gives us the relationship between the triangular numbers and the sequence b sub n. Given that t sub n equals n times n plus 1 over 2, find a sub n and a sub 50. We saw for a sub n in terms of the t sub n earlier. So a sub n we solve for as 5 times t sub n plus the number 4. Let's replace the t sub n with the formula we're given, the handshake formula, which would be n times n plus 1 divided by 2 plus 4. Now this becomes arithmetic. This is fine, but let's clean it up a little bit. For cleaner appearance, we usually factor out the 1/2, okay? Then we'll leave the 5 constant in there, so you have 5n times n plus 1. And when you factor out a half from 4, you're actually going to be multiplying by 2, so it'll be plus 8. Now that's our formula. Then to find the a sub 50, we're going to compute. This is by putting 50 in every place there is an n. So you got 1/2, 5 times 50. And if you don't mind, I'm going to go ahead and do the n plus 1 as 51 plus 8. And at this point, let's just use our calculator to get the output. So you are looking at a TI-84 CE screen. Okay. Let's put the numbers in there. I'll do open parenthesis, put in 5 times, the next number is 50 times 51, and then with that we want to add the constant of 8. So I'll get an output, and then I'll divide that by 2 or multiply by 1/2, and the result is 6,379. Let's transfer that. So a sub 50 is 6,379. Let's do this again. Given that t sub n equals n times n plus 1 divided by 2, find b sub n and b sub 50. We computed b sub n earlier and found b sub n to be t subscript n plus 2 plus 3. So now let's replace. Where the n was, we'll begin with n plus 2. And again, where we had n plus 1, we'll have n plus 2 plus 1. And that will all be divided by 2 plus 3. Okay. We can clean this up a little bit, and we'll end up with n plus 2 times n plus 3 divided by 2 plus 3. That's clean enough. Now let's compute b sub 50. So you're going to put in 50. Every place there is an n. n plus 2, 50 plus 2 is 52 times 53 divided by 2, and then we add 3 to that. Let's use a calculator and do that arithmetic. So again, you are looking at a TI-84 screen. Let's do 52 times 53. Divide that by 2. Add 3 to it, and the result is 1,381. 1,381. Consider the sequence defined for n equal to or greater than 0, the terms 10, 14, 18, 22, and 26. Part A. What is the next term of the sequence? If we look at the gaps, we find out that it is consistent. From 10 to 14 is 4. 14 to 18 is 4. Next two terms is 4. When the gaps are consistent like that, we are dealing with an arithmetic sequence, and that difference is called the common difference. Now, the next term of the sequence, assuming the pattern continues as is, we add 4 to 26, and that would be 30. Now, the next question is, B, what is the nth term of the sequence? And the only thing that we need to be careful of is that this we begin at 0. So 10 actually, let's just make sure we get this, okay? The not term is 10. E sub 1 is 14. The index is a little bit shifted. So if we are looking for the nth term of the sequence, which would be E sub n, okay, that's going to be, well, we start at 10 and add a factor of 4 each time. So we would do 4n, and then let's check. So if I put in n sub 0, I'm checking now. I do E sub 0, then I get 10 plus 4 times 0, which is 10, and it checks with the sequence. So here's the nth term of the sequence. The next is find the sum of the first 100 terms. So here we go. 1 plus 2 plus 3 plus 4. Oh, you don't want to do this all the way to 100? You think there's an easier way? Well, I think you're right. Let's look for a formula. Okay, we will use the summation notation, and we need to add 100, understanding that this begins at 0. So we're going to have the summation notation with the index starting at 0, and we go to 99 because there are 100 items including 0 all the way to 99, and the nth term would be 10 plus 4i. Okay? The formula for this, and instead of just memorizing it, make sure that it makes sense, okay? It's going to be the first term of the sequence, which is 10, plus the last term of the sequence. And the last term of the sequence is e sub 99, or the 100th term is e99. And so that's going to be 10 plus 4 times 99. That's 10 plus 400 minus 4, so that'll be 396. So the 100th term, okay, which is e sub 99, will be 406. So we add the first term and the last term, and you want the average of that. So we would divide that by 2, and then the numbers that you've got, which is n, total of 100. That's supposed to look like 100, not 106. So the rest of it is actual arithmetic computations. We're going to have 50 times, let's see, 416. And when you multiply these two numbers together, you get 20,800. Again, I'm pretty sure you're familiar working with arithmetic sequences. I just wanted to focus on the starting index here for you.